Did you know that some spiders can fly? Well, that is the topic of today's podcast 158. In fact, they can fly so well that they can go as high as 4 kilometers and travel hundreds of kilometers. And in fact, some reports have surfaced that they've been even found 2,000 kilometers out at sea, so over 1,000 miles out at sea. That's better than most birds. But how do they do it? There are two current theories, which we'll be going through. The first is that they shoot their web up into the sky and use winds to catch their web and pull them around. The second theory is that they still shoot their web into the sky, but instead of relying solely on the drag created by winds hitting it, they also use electric potential differences. In other words, their webs become negatively charged or charged to a certain sign, and the ground is charged to the same sign, so typically negative, and then they get repelled away because negative repels negative or positive repels positive. So they use electricity to facilitate this flying. So this second theory has been under much scrutiny, and the major objective is that spiders potentially can't sense the electric fields of the Earth well enough to be able to time shooting their webs into the sky. So for example, well, why do they know to shoot it now and not later? So to find out whether these spiders can do this or not, we are looking at this paper called Electric Fields Elicit Ballooning in Spiders. So they've kind of given away their special source in the title, saying electric fields do, but we're going to go through and look at what they've done to figure this out. And there are some really amazing findings here. For example, just how charged the atmosphere is, even where we are. So for example, like I'm sitting and talking to you here, where my feet are compared to where my head is, can potentially be a 1 kilovolt difference in the charge in the air. I know it sounds ridiculous, but we'll be going through that again in this podcast, and it's really amazing. So anyway, this is an open access paper, and you can find it in the link in the description if you want to play along at home. So now apparently it has been known for quite a long time that some spiders can fly. In fact, even Charles Darwin, or Chuck to his friends, even knew about it. So this phenomenon is called ballooning. And one theory suggests that aerodynamic drag is not the only driver of this ballooning effect. And one criticism that they only use drag is that, well, if they only use drag, then why would these spiders shoot several strands up into the air and then not get them tangled? So when these spiders balloon, when they fly around, they shoot up a bunch of these webs, and instead of getting tangled around with the wind, because like the wind would hit it, and then if it's using drag solely, these strands should all get bunched together and then just mashed together and not stay separate. But in fact, they actually stay separately and actually stay pretty much equidistant away from each other. So that's really only going to be happening if we have electricity when they're charged, because they repel each other. So another criticism of the theory saying that it is just drag is what make these spiders initially take off is that they take off very quickly, which if they took off just with drag, the acceleration wouldn't be as great as what they do experience, especially at low wind speeds. And apparently there are days when spiders fly around in masses, so you can literally just be walking around and have spiders landing on your head. So one thing that is pretty cool is that these researchers call these spiders that fly aeronauts, which makes sense, and I don't know why we don't use this term for ourselves more often. For example, if we fly around for the day, we can call ourselves aeronauts. It's a pretty sweet term in my opinion. And these ballooning effects are most common on overcast days and even on rainy days, which is a little surprising considering that these spiders aren't very big, and I would have thought like getting hit by a raindrop when you're that small would be a pretty big impact for them, but it doesn't. And the plot thickens because a very good predictor for when spiders will do their aeronaut thing is when the wind speeds are below 3 meters per second. So if drag were the main driver of this flight, then you'd think that faster wind speeds would be better for them. But no, the opposite occurs. But one question that comes to mind is the atmosphere electrically charged? I mean, okay, sure, during thunderstorms there's obviously a charge, but on normal or even overcast days, is there any appreciable charge? And yes, apparently, on even a sunny day, so a nice day, like the ones I remember when I was a wee boy, there's atmospheric potential gradient of, on average, 120 volts per meter. So in other words, the average person who's 1.5 meters tall or 1.8 meters tall, or even 2 meters tall, between his or her feet and his or her head, there's a 200 volt difference. And they go on and say that on cloudy, rainy, and even stormy days, this atmospheric potential gradient can be even several kilovolts per meter. So getting hit with a 2,000 volt charge would make you feel alive. And that's effectively what they're telling us. Like the ground on a rainy day or stormy day is 2,000 volts lower than our heads. But I don't know. Like, it doesn't make sense to me, but maybe the amps are so low that we can't even feel it, or maybe it doesn't transmit through our bodies very much, or I don't know why, like, we can't feel it, but apparently that is the case. That there's potentially kilovolts difference between your feet and your head. You just can't really feel it. So, these researchers even say that because plants are pretty good conductors, because they have water and electrolytes, and they are sharply shaped, they can reach tens of kilovolts per meter. And on a little bit of an overcast day, the electric field 10 meters above a canopy of 35-meter tall trees can be over 2 kilovolts per meter as well. So they have a figure here in figure 1, and they have like an oak tree, and then around it the electric field that can actually result from here. So we have like the oak tree is 0 kilovolts per meter, and then when we get to the tops, it's like up to 6 or even 10 kilovolts per meter. So these voltages are huge, so the amps must be really low just to not fry everything. But spiders aren't the only animals actually that might sense electric fields. In fact, bumblebees are known to detect electric fields between themselves and flowers, while honeybees use electric charges to communicate with their hive. So, to test whether spiders can detect and use these electric fields, these researchers devised a setup where they put a spider on a cardboard box, which acts as an atmospheric potential gradient generator, they say, and then the box and the spider is placed in the Faraday cage. And Faraday cages are cool because they are effectively just a bunch of bars enclosing a volume, and if you go inside it and you don't touch the bars, you are insulated from electric strikes because the electricity will just hit the bars and then go around the enclosure and not into you. So that's pretty cool. And this box actually helps the spider feel at home, I guess you could say, because in the wild, spiders typically launch off of trees and branches, something that protrudes from the ground. So because this box is protruding from the ground, it's kind of like the same situation. Now, these researchers said that they used non-conductive, glue-free cardboard to make their launch site triboelectrically neutral. I didn't know what triboelectrically neutral meant, so I looked it up, and what triboelectric means is that apparently that's the charge that forms because of frictions, i.e. like when you slide two surfaces over each other, or like when you were in school and you would rub your soles of your shoes on the ground and then you could shock your friend. So this cardboard box won't produce a charge because of friction. It's triboelectrically neutral. These researchers then created 3 different electric fields. The first was 0 volts per meter, which was the control condition. The second was 1.25 kilovolts per meter, and the third condition was 6.25 kilovolts per meter in the air around the box. Now, these voltages were to replicate overcast and stormy days, as well as electric fields found around trees, grasses, and flowers. So again, you can see these voltage distributions in figure 1, where there is that oak tree and an electric field around it. So it gets pretty crazy. And then these researchers said that this box was then surrounded by a moat to prevent the spider from walking away from the box. So in other words, the only way for this spider to get away from the box was to fly. They had their own little moat keeping it prisoner there for the time of the experiment, which I guess they let the spider away after they finished. So no spiders were hurt in the making of this research, I guess. So there are a couple of indications that for when a spider will begin to balloon. The first indication is that the spider will go onto its toes. So like shown in figure 2a here. Let me zoom in a little bit because it's a pretty cool figure seeing a spider go up on its toes. Now the second indication that a spider will begin to balloon is that it will obviously shoot its web into the sky. And while this web shooting act is a good indication, obviously it could also just mean that the spider is making a web and not trying to fly away. So in reality, the most reliable predictor that a spider will begin to balloon is when it goes onto its toes. I don't even know if a spider has toes, but that's the general idea. They say it's tiptoeing, so it's like on the very edges of their legs. So that is what the researchers were looking for, and they videotaped the spiders to see when they were doing the tiptoeing thing, and that was like, they went, okay, well, if they're doing the tiptoeing thing, then they must be starting to trying to balloon. Now, these researchers found that when they activated their electric fields, the spider specimens tiptoed and a lot more than when there wasn't no electric field. And as the electric field got stronger, so did the likelihood that the spider would tiptoe. That shows that these spiders can not only detect these changes in electric fields, but also that they do use these electric fields to balloon. They do use them to fly around, because if they didn't, then why would they start to tiptoe when the electric field was around? And tiptoeing is only seen when they are about to balloon. So this proves that spiders not only use the wind to help them fly around, but also electric fields, which apparently are incredibly strong even in the area of the atmosphere that we run around in every day. So the final question is, how do these spiders detect the electric field? So pretty cool that bumblebees do it with hairs, which are sensitive to this field. And I guess that kind of makes sense because our own hair, like for me, like I definitely feel like in my hair, like tingly some days. So that's like depending on the weather. And also you can see like some people have frizzy hair on certain days. So it does seem like hair in general is quite sensitive to electric fields. So it seems like the same thing can be concluded here, that spiders seem to use the hairs on their legs, which these researchers have kind of proven as well in this paper, which you can see in figure 3 there, 3b, they're the hair on their legs when they zoom in, and they have like really big thick hairs. So they use these hairs to detect the electric field, and that's not all they use these hairs for, actually. Apparently they also use these hairs to detect the airflow, which could help with their flying as well, so they know like the wind speeds if it's above a certain velocity, like 3 meters per second, not to balloon. If it's below that, then it's okay. But they also use these hairs to detect sound. And with that revelation, we are at the end of this podcast, and it's probably one of the strangest ones we've done, and I liked it. So if you like this as well, give it a like, and if you want to see more like this, hit the subscribe button. And big news, we are just about to release our intermediate CFD course. This course covers pretty much everything you need to literally go into industry and do high quality simulations yourself. We packed it full of information and modules covering everything from how to use RANs, DES, and LES to what different terminus models there are like K-epsilon and SST, and when to use them. So what these mean and why we use them in which situations. We also cover grid convergence and how to do it properly, as well as validation, and even how to do rotating geometries like propellers and wind turbines. That's just to name a few things we covered in this course. There's way more than that in it. So check out this course, which I can almost guarantee that no matter who you are, this course will make you a better CFDer. You also get a certificate once you complete the course to put on your CV and show employers to make yourself more attractive to be hired. So check that course out in the link in the description. And I'll see you next podcast. Peace out, amigos.